smallest thing you could. How does it look in the picture? So there is in the explicit, maybe this is implicit, maybe this is explicit.
That's the way I'm thinking about it.
Yeah, me too. No. So in the explicit thing here, in the space-time, you see a string. But the string starts after the moment that you try to observe it, because it needs time, I suppose. So you see, a point is, once it is a point, really a point, then you see it. But before it's a temporal point, you don't see it in the space-time. But I have another construct by dequantization. So I came from the idea that this non-commutative world is a deformation of a commutative world, which it is, I suppose. So deformation quantization gives you such a picture. Then I wanted to dequantize why? Because if I want to take a pre-sheaf on this whole story here and sheafify, because I don't have enough points, I have to do that in time. But if I want to do that, then I want to construct a sheafification function, which is not possible on the same space. So I made this blow up, if you want, and I blow it down to this thing, and that's the red thing. So what I do is I have these temporal points, and they are points at certain moments, and you get this kind of strange surface here. Remember that this is 4-dimensional, this is, by God, maybe, I don't know what dimension in the non-commutative system, this may be 11-dimensional, whatever. So this is a very simplified picture. But you have, in a certain time interval, and that time interval is the time interval I need to decide on the geometry of the moment t, how far do I have to go in the time interval, let's say, to get all the temporal information from these points to describe the geometry at the moment t. So how much information, how long do I have to observe to have observed the whole geometry at moment t? And that interval, there is a minimal closed interval, this is closed. Many intervals are open. That one is closed. You can take an infinite intersection, and there's a minimal such interval. Now I would suggest it is at the level of the Planck scale. So this is the time, the minimum time that you need to see something at moment t, to have the geometry. But there's many smaller scales where there is a kind of unambiguity. I will talk about that. So in the movement of these spaces, you don't want absolute chaos. You don't want 2 points at a moment t prime to collapse immediately. So immediately means for every time that is bigger, it would collapse. So that they were only different at that moment and never. So in a sense, I want some kind of continuity of the relation, partial order relation, being strictly different. Bigger, for example, but not equal. So if they are related, then they are related over a period of time. And therefore, a strict relation, so one is strictly bigger than another, it has to live in a small, and that's a mathematical, there exists, arbitrary small interval. So there is an axiom, if you want, in the whole theory that says that, okay, if they are different at the moment t, they should stay a little bit like that. They don't disappear immediately. Also, elements can come and disappear. If they're not related to any other element in the non-commutative world, so if there's no other relation except with 0 and 1, the empty set and the whole thing, then they can come and go as they please. But if they relate to something, so in the sense of partial order, but that's an interaction if you want for the physicist, then they should interact in time. And then the partial order has to live in an interval, as small as you want, but in an interval.
But so there's no restriction from the mathematical point of view how small this interval is?
No, this is a mathematical, there it is.
It could be
Could be bigger than the Planck scale, or it could be. I have a number that I want to use sometimes. I was talking about it this morning. It's a very good number to have in mind. That's 1 divided by all the events in the universe. Because the physicists tell me sometimes there's a finite number of events